Come with me, my love, to the sea.
Welcome to the video on optimization in several variables. So first of all, what is optimization? So to optimize something, or I'll just say that optimization is, it's the process of finding extreme values of a function. So process of finding extreme values, aka extrema, of a function. Okay, and extreme values meaning minimums or maximums. Okay, so this is like a min or a max or both. Okay, and that's basically it. So like minimum or maximum, minimum being the lowest point on a graph over a certain like domain or domain, domain, and then maximum being the highest point within some range of like your x or y coordinates. Okay, so there is a difference between local extrema versus global extrema. So local versus global. So local, as the word might imply, local is more like concentrated in a small area. So that basically means like your f of a b, that your function, this point here is a maximum or minimum, a local maximum or minimum in some small open disk around AB, around the point AB. Okay, so that just means within a tiny little vicinity. So here's your point AB. So within some small circle here, so this disk, then our function is a maximum at that point P, which is AB, something like that. Okay. All right, and then global, the difference here is that something is a maximum or a minimum, a global maximum or minimum value, if it is the maximum or the highest or lowest point on a given domain, D. Okay? Alright, well, we'll go over the difference more or less as we go along on this video. I just want to show you guys like what, just give you a brief introduction as to what the difference is conceptually. Okay, so we're going to start with local values, or local extrema. So we're going to start with local extreme values. Okay, so we're looking locally. So this means that, let's say we start with a local maximum. Okay, so local maximum. I'll just abbreviate here. Okay, so let's say we have a graph. Like here's our x, y, and z coordinates, and we have something looking like sort of like a mountain range. Right, so some surface like that. Okay, then it continues off in either direction there. Okay, so let's look at this point here. Okay, so this point at the top of the small hill, we're going to call this, this is f of p. Okay, this is our f of x, y graph. That's the surface. Okay, and f of p means that our p is on the xy plane. Okay, and has coordinates a, b, or something like that. Okay, and so basically, when we're looking at local things, we look at like a small disk right around the point on the xy plane. Okay, so everything around here, all of these points, when we kind of like transfer them up and plug them into the f of xy graph or the surface, everything else around this point is below it as far as like the z, the height goes, right? So this one is a local maximum because, more formally, f of xy, all of the f of xy, the height is less than or equal to f of ab, and ab being our p, our point p, so p is ab. Okay, so all of the other values, all of the other heights around this point are less than that height for all xy coordinates, so on the xy plane. Within the disk, this means disk of center P and radius R. Okay, so center P and radius R would be like something very small. Okay, so the radius is very small. Okay, alright, so that's basically what it is. And now for the local minimum, we'll go over that one. It's basically going to be the same thing, or at least very similar. So minimum. Okay, and so a picture of this one would look like kind of like the other one, except for now instead of a mountain, we have a valley kind of thing. So this one, it's a little bit harder to draw. Let's draw something like this, and then it comes back up, okay? And it's on a surface, okay? So it's going like that, sort of. Right? So we're going down, the surface is going down, alright? It's kind of like a pit, okay? It actually looked pretty good. So anyways, so here's our f of xy, right? Let's say this is our point f of p. And if we draw down, then we get, this is the point P on the xy plane, okay? And this is AB, P equals AB, all right? So here we see that, let's look at the disk around P, okay? So this is the disk of center P and radius R. So our radius is like something like that, okay? And so formally a local minimum is denoted when our f of xy, so the height of our surface, okay, is greater than or equal to the value of our function at that point, AB or P, right? For all xy within that disk, the disk surrounding P with radius R, okay? And that's basically it. So it's just saying that at all of the other points right around P, the surface is higher than or is above the value of our function at P. Okay, so everything else is above it up here. All right, so that's basically it. So that's what it is conceptually. And now, like, what are we supposed to do with all of this information? So what I'm going to do is we're going to kind of like throw back to a single variable calculus. So in one variable calculus, when we have a local maximum or minimum at a local max or min, there is a critical point, basically. So there's a critical point. Here's a critical point, okay? Meaning that, like, let's look at a graph, first of all. So let's say we have some graph going along, and it looks like that, okay? So here's a local maximum, and here's a local minimum. So these are critical points, and additionally, more importantly, the tangent line and the tangent line at each of those points, so tangent line is horizontal, right? It has a slope of 0, is horizontal. So at that point and at that point, they're both horizontal, okay? So that's pretty important. And now what we're going to do is kind of extend this concept to multivariable calculus. So in multivariable calc, what we'll have at a local max or minimum, so at local max or min, we're going to kind of have the same thing. It is called, there's called a critical point. So there's a critical point, critical, and then point. And now let's look at the picture. So if we draw in 3 dimensions, because that's where we're living right now, so let's say there's a surface here, okay, and this is our maximum point, okay, and actually at that point we don't just have one line, but now we have what's called a tangent plane, okay. So this tangent plane must be horizontal. So now we have, and the tangent plane, okay, is or must be is horizontal. Okay? All right, so slowly but surely we're getting there as to what I'm getting at here. So the tangent plane being horizontal, let's see what that means. So here's a tangent plane. And the equation of a tangent plane is given by the linear approximation, right? So z is equal to f of ab plus f sub x at ab times our x minus a plus f sub y, that's a y, f sub y, at ab times y minus b. Okay, so for this tangent plane to be horizontal, that means that the slopes I guess the slope of it, it can't be tilting upward or downward in any kind of direction, right? So what we want is we want the tangent plane to have a slope of 0, which means that the height is constant, okay? We want height to be constant. We want that to be a constant. So that means that z has to equal a constant. Z represents the height, right? So we want that to be constant and not changing. So that means that our slopes are 0. So that means that we require that our f sub x and f sub y are either 0 or they do not exist, okay? So we want our fx at AB and equal to f sub y at AB, which is equal to 0. Okay, so this is one way for our z to be a constant, right? That way then z is only equal to f of AB, which when we plug that point in, that'll definitely be a constant, right? So this is a constant, so that's good. So what we're finding is what is the definition of a critical point in multivariable. So what we have is a critical point, AB, okay? So when this happens when our f sub x of AB is equal to 0, or when it does not exist, okay? We always have to include that possibility there, keep that in there. And at the same time, our f sub y of AB also has to either equal 0 or not exist as well, okay? Or either, I guess, either, okay? So that's what we have to have. At the same time, both our f sub x and f sub y either have to equal 0, both equal 0, both not exist, or one equals 0, one doesn't exist. And one of them has to be, or they both have to be one of these options, okay? Like one of them can't just be 2 or something, be the number 2 or whatever, what have you. So these are the conditions for there to be a critical point, and then we could have a local minimum or maximum, or maybe nothing. Critical point just means something might be going on at that point. Okay? Alright, so now we found how to, like, what's the criteria for a critical point, right? Now we're going to determine what type of critical point it is. Whether it's a local maximum, local minimum, or maybe even nothing.
Do